I'm Dr. B. Shailaja. I'm going to explain Lorentz transformations. Let us consider we have two frames of reference S and S prime. S is a frame which is at rest and S prime is a frame is moving with a velocity v along the positive x direction relative to the frame S. Let t and t prime be the times recorded in the two frames. For our convenience, let us consider the origins O and O prime coincide at t equal to t prime equal to 0. Let us consider we have a source of light is situated at the origin O in frame S. So this source of light will emit wavefront at t equal to 0. When the light reaches the point P, the position and time can be measured by the observer O can be written as x, y, z and t. The position and time measured from the observer O prime can be written as x prime, y prime, z prime and t prime. If the velocity of light is c, then the time measured by light signal in traveling a distance OP in frame S can be written as t equal to OP by c, which is equal to root of x squared plus y squared plus z squared over c, or this equation can be rewritten as x squared plus y squared plus z squared equal to c squared t squared. This equation is called as the equation of wavefront in frame S. According to the special theory of relativity, the velocity of light will be c in the second frame S prime. Hence, in frame S prime, the time required by the light signal traveling a distance O prime P prime can be given as c prime, which is equal to O prime P by c, which is equal to root of x prime square plus y prime square plus z prime square by c. Or this equation can be rewritten as x prime square plus y prime square plus z prime square is equal to c square t prime square. This is called as the equation of wavefront in frame S prime. The transformation relations relating to x, y, z, t and x prime, y prime, z prime, t prime should be such that equation 1 gets transformed to equation 2. The Galilean transformations connect the measurements in two frames according to the following equation. X prime is x minus vt, y prime is y, z prime is z, and t prime is t. Substituting these values in equation 2, we get x minus vt the whole square plus y prime is y, therefore y squared plus z squared minus t squared because t prime is equal to t. So when we expand this, we get this equation x squared minus 2x vt plus v squared t squared plus y squared plus z squared minus t squared t squared. So when we compare these two equations 3 and with that of 1, these two are not equal. So we get two extra terms which are minus 2x vt plus v squared t squared. Thus, the Galilean transformation fails. When we compare equation 1 with that of 3, we'll be able to see that the y and z are in agreement. Hence, y prime is equal to z, y, z prime is equal to z. But the two extra term minus 2x vt and the plus v squared t squared indicates that there is a transformation in x and t. Should be modified. So when we know that the observer O, the distance O prime is equal to vt. Therefore, when x prime is 0, x is equal to vt. Therefore, the transformation can be written as x prime is equal to alpha into x minus vt. Now, this t prime is different from t and may depend upon x. Therefore, we can write t prime to be equal to alpha prime into t plus fx. So here alpha prime and f are constants. Substituting these values of x prime, y prime, z prime, t prime in equation 1, we get alpha squared into x minus vt the whole square plus y squared plus z squared is equal to t squared alpha prime squared t plus fx the whole square. So expanding this this is of the form a minus b the whole square. So expanding, we get alpha squared into x squared minus 2x vt plus v squared t squared plus y squared plus z squared is equal to c squared alpha prime squared into, expand this again in terms of a plus b the whole square, we get this equation. So here in this equation, x squared terms can be grouped together. So x squared into, the coefficient of x squared here is alpha squared, so alpha squared, and the coefficient of x squared is f squared into c squared alpha prime squared. So when you take it to the other side, it's going to be minus f squared c squared alpha prime squared. So we have grouped the coefficient of x squared now. So now we'll try to find the coefficient of 2xt. So in this term, the coefficient of minus 2xt is alpha squared v. Okay, we got the alpha squared v. And the coefficient of 2xt is c squared alpha prime squared f. So when we take it to the other side, it's going to be minus. So we have taken a minus common. So it's going to be plus f c squared alpha prime squared, followed by y squared plus z squared, and the coefficient of c squared t squared in this side is alpha prime squared. Okay, so here this is going to be alpha prime squared. The coefficient of c squared t squared, we don't have c squared, so we have to divide it by c squared, followed by alpha squared v squared. So the coefficient of c squared t squared here will be equal to alpha squared v squared by c squared. Let's name this as equation 4. So now let us compare this equation 4 with that of 1. The coefficient of x squared and c squared t squared is 1, and we don't have minus 2xt term. Therefore, this term can be equated to 0, and this term can be equated to 1. Obviously, this term can be equated to 1. So let us name this term as equation 5, this mid one as equation 6, the last can be called as equation 7. From equation 6, f has to be determined, so f is found to be equal to minus a squared v by a prime squared c squared. Substituting the value of 8 in equation 5, this equation, and simplifying, we get this 1 minus alpha squared v squared by c squared alpha prime squared is equal to 1 by a squared. From equation 7, alpha prime squared can be written as 1 plus this term. Now we'll substitute the value of alpha prime squared from this here, and simplifying, we get alpha to be equal to 1 by root of 1 minus v squared by c squared. Substituting value of alpha in this equation, we can get the value of alpha prime squared, and alpha prime squared is also equal to alpha, which is equal to 1 by root of 1 minus v squared by c squared. So now let us substitute the value of, since alpha prime squared is equal to alpha squared, this can be eliminated, so f can be written as minus v by c squared. Therefore, substituting the values of alpha, alpha prime and f in 5, 6 and 7, we get x prime to be equal to x minus vt by root of 1 minus v squared by c squared, y prime is y, z prime is z, t prime is t minus vx by c squared by root of 1 minus v squared by c squared. So now let's just assume this v by c squared to be beta, v by c to be equal to beta, and gamma to be equal to 1 by root of 1 minus v squared by c squared. Then we can write this whole equation as x prime to be equal to gamma into x minus vt, y prime is y, z prime is z, and t prime is gamma into t minus vx by c squared. So this equation is what's called as the Lorentz transformation equation. If s prime is moving with a velocity minus v in the negative x direction, then the transformation equations can be called as the inverse Lorentz transformation equation. So here x will be equal to gamma into x prime plus vt prime, y is to be equal to y prime, z is equal to z prime, and t is equal to gamma into t prime plus vx prime by c square. So this equation is what is called as the inverse Lorentz transformation equation, and the first one is what's called as the Lorentz transformation.